Something just woke up under the Pacific, and it is older than the dinosaurs. About 250 miles beneath the ocean floor, in a dark and crushing layer of rock that no human has ever touched, a hidden piece of ancient seafloor has begun to show itself to scientists for the very first time. It had been buried there for more than 100 million years, swallowed by the earth long before the first flower ever bloomed. And yet, somehow, against every expectation, it is still there. It kept its shape. It kept its cold. And now it is whispering back to us through the ground itself, telling a story that nobody ever expected to hear. What you're about to learn will change the way you imagine the ground beneath your feet, because the ground is not what you think it is. It is not quiet. It is not still. It is not finished. It has memory, and right now that memory is waking up. To understand why this matters, you first have to picture what the inside of the earth actually looks like. Most people imagine a hot yellow liquid ball beneath our feet, like the inside of a melting chocolate truffle. That picture is wrong in an important way. The earth is made of layers, like an onion, and each layer behaves in a different way. The outermost layer is the thin skin we live on. It is broken into pieces called tectonic plates, the same plates that carry the continents and the ocean floors around the surface of the planet like slow puzzle pieces drifting on a conveyor belt. Beneath that thin skin lies a deeper, thicker layer called the mantle, which makes up most of the Earth's volume. The mantle is not liquid. It is solid rock, but it is so incredibly hot and under so much pressure that it behaves like soft clay over long spans of time. It can slowly flow, it can buckle, it can crack. And right in the middle of the mantle, about 400 miles down, there's a strange boundary called the mantle transition zone. In that thin band of rock, minerals in the earth suddenly rearrange themselves into new crystal shapes because the pressure becomes so high. Water, in chemical form, can be trapped inside those crystals like moisture locked inside a sponge. It is not the water you would drink. It is water inside the molecular structure of the rock itself, held prisoner by heat and pressure. Now the surface of the earth is constantly being recycled. Old ocean floor slides down into the deep at places called subduction zones, where one tectonic plate dives beneath another and sinks into the mantle. When an ocean plate sinks, it carries water and minerals down with it, and most of that material slowly melts back into the deeper earth over time. Scientists have always assumed that this process destroys the old seafloor completely, like an old letter thrown into a fire. There would be nothing left to find. But that is what they assumed. They did not know for sure. And what they have just discovered has rewritten one of the quietest assumptions in all of geology, because deep beneath the Pacific, something ancient refused to melt at all. In the year leading up to this discovery, a team of researchers at the University of Maryland, working with collaborators in Europe, began building a far more detailed picture of the deep Pacific than had ever existed before. The lead scientists behind the work were geophysicists Nicholas Schmer and Vedran Lekic, who had spent years trying to listen to the Earth the way a doctor listens to a heartbeat through a stethoscope. They used a network of more than 200 seismic stations, the same kind of stations that detect earthquakes, scattered across the United States and around the Pacific Rim. Every few months, when an earthquake shakes somewhere in the world, the vibrations from that earthquake travel through the earth and bounce around inside it like sound waves inside a cathedral. By recording those vibrations at hundreds of different points on the surface, and by combining thousands of those recordings with painstaking mathematical modeling, scientists can build a kind of ultrasound image of the interior of the Earth. In the same way doctors can see a baby inside a mother, these researchers can see structures inside the planet that nobody has ever visited. The process is slow, it is careful, and it is one of the most powerful tools we have for studying a part of the world we cannot touch. What they saw when they finally put the image together was a feature that nobody had ever imaged clearly before. Buried about 250 miles beneath the surface, sinking deep into the mantle transition zone underneath the Pacific, was an enormous, cold, dense slab of rock that should not have been there. It looked like a wrinkled piece of original ocean floor, still intact, still cold, still recognizable, even after more than 100 million years of being swallowed by the Earth. Its weight had pulled it downward. Its coldness had kept it from melting. And because it was chemically different from the rock surrounding it, the seismic waves passing through it moved at different speeds. That difference was the giveaway. That is how the scientists knew something was hiding. It is, in plain terms, the same way you can guess there's a metal hinge inside a wooden door, because the sound of a knock changes when your knuckle lands on it. The Earth knocked, and the scientists listened, and the answer came back flat and heavy and strange. The researchers published their findings in the journal Science in 2024, and the title of their paper was deliberately careful. They did not claim to have discovered some brand new continent. They did not talk about a lost city. They wrote, in plain scientific language, that they had found evidence of a subducted oceanic slab that had been preserved in the mantle transition zone since the Mesozoic era, which is the age of the dinosaurs. Let that sink in for a moment. The age of the dinosaurs. We are talking about a piece of seafloor that was sliding into the earth while T-Rex was still alive. And it is still there. It is still cold. It is still carrying its original water and its original minerals down into the heart of the planet. Now here's the part that should make your skin prickle a little, because the slab is not just sitting there inert, like a fossil pressed in a book. Its weight is pressing down. Its coldness is changing the chemistry of the rock near it. And because the mantle transition zone is exactly the part of the Earth where water can be locked inside crystals of a mineral called ringwoodite, the slab is potentially feeding water into a vast reservoir that we did not know existed until recently. Ringwoodite is a mineral that only forms under the enormous pressures found a few hundred miles below the surface. Its crystal structure is unusual because it can hold water inside it, not as a liquid pool, but as hydroxyl ions woven into the rock itself. Estimates by researchers at institutions including the University of Hawaii and Stanford have suggested that the mantle transition zone could be storing an amount of water equivalent to the volume of all the surface oceans combined, locked inside solid rock. Some estimates go even higher. If that turns out to be true, then there is more water inside the Earth than there is in every ocean, lake, and river on the surface, and most of us never knew. So when this newly discovered ancient slab sinks into that water-bearing layer, it is not just dropping into empty rock. It is dropping into a vast chemical sponge. That has consequences. The water content of the deep mantle influences how easily rock melts into magma. It influences how plumes of hot material rise toward the surface. It influences why some volcanoes are violent and explosive while others are gentle and runny. It influences the formation of diamonds, because diamonds form in the very same depth range. And many diamonds that we mine carry tiny mineral inclusions that record the chemical fingerprint of the deep mantle water cycle. The slab that just woke up beneath the Pacific is, in other words, not just a curiosity. It is part of a plumbing system that shapes volcanism, ocean chemistry, sea level, and the slow geological heartbeat of continents. But that is not the only reason this discovery has shaken scientists awake at night. The other reason is this. The slab should have been destroyed. According to the textbook picture of how the Earth works, a slab that old should have heated up by now, lost its coldness, mixed back into the surrounding mantle, and become invisible. Instead, it is still cold enough and dense enough to leave a clear, sharp image in seismic tomography. That means either our models of the deep Earth are missing something important, or there's a process we have not yet discovered that allows ancient slabs to survive much longer inside the planet than anyone previously believed possible. And that single fact is enough to disturb an entire generation of geological textbooks, because if even one slab can survive 100 million years, then the deep Earth is not the slow mixer we always thought it was. It is, in places, a museum. It keeps its old things, it preserves them. And if a Pacific slab can be preserved, then maybe other old slabs can too, hidden in other parts of the mantle, waiting to be imaged. Let that question sit with you for a moment. How many more ancient slabs are sitting beneath us right now, completely unknown, completely unimaged, simply because nobody has yet pointed enough seismic stations at the region above them to detect them? The truth is, we have only just begun to look. To understand how the researchers actually found this hidden slab, it helps to know a little more about the technology that made it possible. Just a few years ago, most seismic images of the deep Earth were blurry. They were useful, but they were blurry in the way a low-resolution photograph is useful. You could see blobs, you could see general shapes, you could see vague edges where something denser or colder or hotter than the surrounding rock was hiding, but you could not see detail. And then, beginning in the early 2020s, a new generation of dense seismic networks was deployed across North America and other regions. The largest of these was a project called US Array, which systematically marched hundreds of portable seismometers across the United States over a period of years. Combined with permanent stations, ocean bottom seismometers placed on the seafloor, and a growing cloud of European stations in the Pacific region, the dataset suddenly became rich enough to let scientists see features at far higher resolution than before. The same way digital cameras replaced blurry film cameras, modern seismic tomography replaced blurry tomographic maps of the past with something sharper and far more revealing. The transition from old maps to new ones is one of the quiet revolutions in earth science, and most people outside the field have no idea it even happened. When the University of Maryland team fed the new data into their models, the picture that emerged was breathtaking. There, in the mantle transition zone directly beneath the Central Pacific, was a structure the scientists described as a drip-shaped mass of cold, dense rock that had remained stable for at least 100 million years. The structure was not random. Its position lined up almost perfectly with a known pattern of intraplate volcanoes on the Pacific seafloor, called hotspots, where molten material rises from great depth and pokes through the crust to form volcanic islands and seamount chains. Famous examples include the Hawaiian Islands, Famous examples include the Galapagos. Famous examples include Samoa. And here is the deep connection that Earth scientists find so tantalizing. The cold slabs sitting in the transition zone may be helping to feed those volcanoes, sitting there for hundreds of millions of years, slowly releasing water and changing the melting behavior of the mantle right above it. In other words, the cold slab is not just dead weight. It is possibly the long-term engine that has powered an entire chain of Pacific islands. Let yourself feel the scale of that for a moment. The Hawaiian Islands are some of the most isolated volcanic chains on Earth. They rise out of thousands of miles of empty ocean. The Pacific Plate has been slowly drifting northwest over a stationary hotspot for tens of millions of years, and as it does, successive volcanoes form, drift away, become extinct, erode, and sink back beneath the waves, leaving behind a long ribbon of islands and seamounts stretching across the floor of the ocean. Above the new slab, that pattern may be even older and deeper than anyone thought. The same chemical fingerprint, the same volcanic style, the same long-lived plume of melted material rising through the mantle could be traced back to a slab that began sinking into the Earth in the Mesozoic. If true, then volcanoes today are still writing a story that began in an era of giant reptiles, when continents were arranged in configurations that would look utterly alien to us now. The past is not past. It is alive, and it is doing work right now beneath our feet. The lead scientists were careful in the way serious scientists are always careful. They did not rush to claim that every hotspot above their newly imaged slab is connected to it. They noted the correlation. They published the data. They invited the community to look, and as soon as they did, other groups began to investigate. Within months, similar studies began to appear using different data sets, sometimes arriving at slightly different conclusions, which is how science is supposed to work. Not every paper has agreed on the exact shape or depth of the slab. Some have argued that the structure may be older or younger or a little shallower or a little deeper. But the core finding, the existence of a preserved slab of ancient seafloor at that depth, has held up under scrutiny. Multiple independent teams, using different seismic data sets and different tomography methods, have found the same general feature in the same general place. That replication matters enormously. In science, a single claim is just a claim. A claim that survives multiple independent retests begins to look like a fact. And here is where the script turns, because we now arrive at a strange realization. Hidden beneath that famous image of the Pacific Ocean, full of its sunsets, its beaches, its blue surface beauty, lies a world that is far more layered, far more active, and far older than the surface implies. The Pacific Ocean covers more area than all the continents combined. Beneath it sits the largest tectonic plate on Earth, one that has been grinding, sliding, slipping, and absorbing ocean floor for hundreds of millions of years. Beneath that plate sits the mantle, layered like a colossal lasagna, with each layer doing its own slow chemistry. And beneath that mantle sits the transition zone, the band of rock that may hold more water than all our oceans. The discovery of an ancient slab beneath that transition zone is not just a single geological headline. It is a window into an entire hidden world that has been working in silence since long before the first dinosaur hatched. Now, let us rewind for a moment, because the emotional weight of this story really comes from contrast. Think about the scale of human life. A human life lasts around 80 years. A civilization lasts around a few thousand years. A species lasts around a few million years. A slab of ocean floor, sitting quietly under the Pacific in the dark, has been there for 100 million years, give or take. It has been there longer than the Rocky Mountains. It has been there longer than the flowering plants. It has been there longer than bees. It has been there longer than grass, longer than songbirds, longer than whales. And it has been doing chemistry the entire time, slowly, in silence, with no witnesses, until now. The contrast between the brief, flickering timescale of human life and the heavy, slow, almost endless timescale of geology is one of the most humbling things we can contemplate. We tend to think of the Earth as a backdrop for our stories, a stage that has always been there and always will be. What this discovery tells us is that the Earth is itself a story, an ongoing one, and with characters we cannot see, and a timeline that dwarfs our own by several orders of magnitude. We are not the main character of this planet's history. We are a recent paragraph in a very long book, and the chapters before us are still, even now, shaping what happens next. There's also a quieter, more personal reason why this story matters. The slab beneath the Pacific is part of the same global system that produces earthquakes, tsunamis, and volcanic eruptions along coastlines that some of us call home. The Pacific Northwest, where the United States meets Canada, sits above a subduction zone called Cascadia that has been the focus of intense scientific concern for years. The team of researchers at the University of Maryland, who discovered the ancient Pacific slab, have spent years studying Cascadia at the same time, mapping the geometry of the subducting plate that lies beneath Oregon and Washington. Some of their other discoveries, published in the same period, include the surprising finding that stress on the Cascadia megathrust fault The fault that could one day produce a massive earthquake may actually be released in smaller stepwise slips rather than one giant event. That is significant because it changes the calculus of risk and preparedness. If the giant earthquake is less likely to come in one catastrophic moment, but more likely to come as a series of smaller events, then the entire planning model for the Pacific Northwest has to adjust. Insurance rates, evacuation plans, building codes, hospital readiness, these are not abstract geophysics. They are concrete decisions about real cities, real people, and real lives. So when scientists pull back the curtain on a hidden slab buried a few hundred miles under the Pacific, it is not simply an academic exercise. It is work that informs everything from how we build schools, to how we forecast volcanoes, to how we prepare coastal towns for the next big shake. And that brings us naturally to one of the more dramatic threads in this story. Right now, off the coast of Oregon, there's a submarine volcano called Axial Seamount that is behaving in a way that has gotten the attention of volcanologists around the world. Axial Seamount is the most active submarine volcano in the northeastern Pacific, and it sits on top of a hot spot of magma just beneath the seafloor. For years, scientists at Oregon State University, including researchers like William Chadwick, have been carefully tracking its swelling. The seafloor above the volcano literally rises as molten rock fills chambers beneath it. By comparing how high it has lifted and how quickly it has lifted, scientists can estimate when pressure inside the magma chamber will exceed the strength of the surrounding rock and trigger an eruption. In 2024 and 2025, the seafloor above Axial Seamount was rising faster than at any other time in the recent record, suggesting that an eruption was imminent. Many forecasts suggested that the volcano would erupt in 2025. It did not. The rate of inflation slowed. The threshold was not crossed. And so the scientific team cautiously updated their forecast, pointing to mid to late 2026 as the most likely window. Axial Seamount is now considered the most likely major eruption candidate anywhere in the United States in the next year or two. It is being watched in real time, around the clock, with instruments that send data up to satellites and back to shore. The reason Axial Seamount matters in our story is that it sits above the same general plumbing system that connects the surface Pacific to the mantle transition zone far below. Magma-feeding Axial Seamount has to rise through the same oceanic crust, the same mantle wedge, and perhaps draw on the same deep water chemistry that we just described in the ancient slab discovery. If a slab from the Mesozoic era is feeding water and altered minerals into the lower mantle today, and if that water-rich region melts and feeds volcanoes like Axial Seamount, then a future eruption off the Oregon coast is not just a local geological event. It is a release of pressures and chemistries that have been building inside the Earth since the time of the dinosaurs. You, sitting on a beach in California, or in a school in Seattle, or on a fishing boat in the Gulf of Alaska, are connected by chemistry and by physics to a piece of seafloor that began sinking under the Pacific when T-Rex was small. That is not poetry. That is the system we live inside. Now think about what that means for the future. If the ancient slab beneath the Central Pacific is still feeding water into the transition zone, and if the transition zone truly contains a vast reservoir of bound water, then the slow, persistent release of that water over millions of years has consequences for the entire ocean system. Some Earth scientists have suggested that this is the long-term reason why Earth's oceans have maintained a relatively stable volume for at least 4 billion years, despite constant loss of water to space and constant deposition of water into the deep mantle. The ocean is not just a static veneer over the planet, it is possibly the surface layer of a much larger water cycle, much of which is happening invisibly under our feet. Every wave that crashes on the shore could be part of a cycle that includes water that was once locked inside the Earth for 100 million years. That thought alone is staggering. But the discovery goes further. The newly imaged slab directly challenges the model that says all subducted material is rapidly recycled. It suggests that the deep Earth is not a great melting pot that mixes everything together quickly. It is more like an archive. Different things preserve at different depths, for different lengths of time and under different chemical conditions. Some things get smashed and remade within a few million years. Other things can endure, cold and intact, for 100 million years, like a postcard preserved at the bottom of a frozen lake. And whether a thing endures or disappears depends on tiny details of pressure, temperature, mineralogy, and water content. This means our old textbook picture of the mantle, a slow, mostly homogeneous blender of rock, is incomplete. The mantle is layered, both physically and chemically, in ways we are only beginning to appreciate. This is why the discovery has come as such a shock to the community. For decades, the standard textbook explanation of how the deep Earth works has been simple, clean, and elegant. Ocean floor forms at mid-ocean ridges, spreads outward, cools, slides beneath continents at subduction zones, sinks into the mantle, melts or mixes in, and is eventually returned to the surface through volcanoes. The cycle repeats. The cycle has repeated for billions of years. There was no obvious need to suspect that any piece of that cycle could pause for 100 million years in the middle, resting comfortably at depth, like a sleeper in a long dream. Now we know it can. The cycle can pause, the cycle can stall. And the implication is that the textbook is going to have to be rewritten in a careful, slow, careful way, with new additions, new diagrams, new chapters, and a new glossary term for preserved slab. Before we close, let us also note one more profound consequence. The same imaging techniques that revealed the ancient slab beneath the Pacific are now being deployed to look elsewhere. Other teams, working with similar datasets, are now hunting for similar preservation features beneath the Atlantic, beneath Africa, beneath the Indian Ocean, and beneath the oldest parts of continents. Each new find reshapes the picture. Each new find adds a new constraint. Each new find tells the community something it did not know. And as the resolution of seismic tomography continues to improve, and as more ocean bottom seismometers are deployed, the picture of the deep Earth will keep getting sharper year after year. Decades from now, the maps will look very different from the maps of today, and the textbook diagrams will have new colors, new labels, and new surprises that no one has seen yet. There is one more layer to peel back, because this is the part that made the original team of scientists sit very still when they saw the image for the first time. The Pacific slab they found does not sit in isolation. It is one feature in a vast, mostly hidden continent of dense rock resting at the base of the mantle transition zone, a continent made of similar cold leftovers from vanished oceans that have piled up there like ships frozen in harbor ice. Scientists call this pile by various names, including the slab graveyard, and they have spent more than 2 decades arguing about what it is, how it forms, and why it sits where it does. Some argue it is the resting place of nearly every ocean floor that has ever subducted in the last 250 million years. Others argue that much of it is actually primordial material that has been down there since the Earth first formed. The new Pacific discovery sharpens both debates because a slab that has demonstrably survived 100 million years without melting becomes, in effect, a proof of concept. It shows that long-term preservation really is possible. It shows that the slab graveyard is not just an idea. It is a real, observable place full of real, observable things that came from the surface and refused to disappear. Every Pacific ridge that ever opened and closed, every micro-ocean that ever vanished in a closing trench, every small ocean basin that ever disappeared when 2 continents collided, may have left a piece of itself down there in the dark. The deep Earth, in this picture, is a vast attic full of old worlds. Here is where the script bends again, because the now famous Pacific discoveries do not stand alone. They are part of a wider moment in Earth science in which our picture of the deep mantle has been quietly rewritten by a combination of new seismic data, new mineral physics experiments in high-pressure laboratories, new computational models run on supercomputers, and new ocean floor drilling campaigns that can sample rock directly. In laboratories, scientists squeeze tiny samples of analog rock between the tips of diamond anvils, replicating the pressures of the deep Earth, and then watch how minerals behave, how water gets stored, how crystals rearrange, and how melting points shift. Those experiments have shown that ringwoodite can hold up to about 1.5% water by weight, which sounds tiny, but turns out to be enormous at planetary scale. Multiply 1.5% water across the entire volume of the mantle transition zone, and you get numbers large enough to fill several Pacific oceans, hidden inside rock we walk over every day without thinking twice. This is not fantasy. This is the result of real measurements, replicated by separate teams using separate samples, and consistent with the rare natural diamonds that occasionally bring up tiny inclusions of high-pressure minerals from those depths. The diamonds are made in the slab graveyard. They are messengers from the deep. And here is the strange, almost reflexive question that every thoughtful person eventually asks when they first hear this story. If the Earth is hiding so much water so deep down, and if ancient slabs can survive that long, could there also be chemical richness down there that we have not yet imagined? Could there be pockets of unusual rock with unusual chemistry, with unusual mineral species that do not exist on the surface? Could there be deep reservoirs of carbon, locked away since the dawn of the planet, slowly exchanged with the surface through volcanoes? Could there be ancient helium, ancient argon, ancient carbon dioxide, ancient methane, all packaged inside a slab that has been there since the Cretaceous? The honest answer is that we do not know. We have only just begun to look, and what we are finding is already stranger than the textbook expected. The richest philosophical response, the one that fits the evidence, is humility. The Earth is bigger, older, and more surprising than our textbooks. It always has been. What this means for everyday life is worth pausing on. Volcanologists now use slab images, hotspot locations, and transition zone hydration estimates to refine their forecasts of future eruptions on the Pacific Rim, from the Andes to Kamchatka to Japan to the Cascades. Earthquake hazard teams use similar models when they estimate how stress builds up along locked subduction megathrusts. Climate scientists studying deep carbon and water cycles use the same data to refine long-term projections of sea level and atmospheric chemistry over the next 100,000 years. The slab that woke up under the Pacific is not just a curiosity for a few geology enthusiasts. It is one of the inputs that quietly shapes how the 21st century will unfold along the most populous, most volcanic, most seismically active ocean basin on Earth. That is the part of the story that touches you, even if you live far from the Pacific. Every coastline on that ocean is downstream of the same deep plumbing that this slab now belongs to. Places like Tokyo, Manila, Jakarta, Lima, Santiago, Anchorage, Seattle, and yes, even small atolls in the middle of the ocean, all sit above the same general subduction machinery. If a deeply buried Mesozoic slab can change how melting happens in the mantle beneath Hawaii, it can change how melting happens beneath any one of those regions, in ways that scientists are racing to map in higher resolution than ever before. Now think about what happens the next time you go to the ocean and look out at the water. You will see waves. You will see a horizon. You will see a deep, calm, endlessly shifting blue, and somewhere beneath that blue, 250 miles down in the dark, a piece of seafloor older than flowers, older than mammals, older than any human ancestor we would recognize, is hanging in the rock like an old photograph in a forgotten album. It is not moving. It is not melting. It is just sitting there, hidden, ancient, patient, while we walk around on the surface, completely unaware of it. Until now. Until a team of researchers pointed instruments into the earth and listened to the knock on the door, and the answer came back, and the door opened a crack. And on the other side, there's a piece of a lost ocean, still cold, still intact, still telling its story to anyone who knows how to listen. This, then, is the larger meaning of what was found. Not just one slab, not just one chapter, but a confirmation that the deep earth holds its past much more carefully than we believed. Every time a new seismic array goes online, every time a new tomography study comes out, every time an ocean bottom seismometer feels the ring of a faraway earthquake, we have a chance to catch the faintest echo of another forgotten thing down there. Some of those echoes will be old seafloor. Some will be old continents. Some will be old minerals we have never seen on the surface. Each new echo is a piece of the past, waking up. What you have just heard is the quiet end of one of the loudest geological discoveries of our generation. The Pacific is not what it looked like an hour ago. The ground beneath it is older, more layered, and more alive with memory than the textbook said it could be. Something did wake up under the Pacific. It is real. It has 100 million years of patience, and it is still telling its story. Listen, and the Earth will keep talking. The next chapter of the story has not been written. The Earth is still keeping its secrets. And somewhere, right now, a graduate student in a lab is running a new analysis, and the image on their screen is beginning to take shape. And beneath that image, a new piece of the past is beginning to wake up.